Yeah. So I'm Sihao Cheng. I'm a postdoc member at Institute for Advanced Study and the Perimeter Institute. And today I'm going to talk about some planet candidates around massive white dwarfs. After 30 years of search for planets, how much do we know about exoplanets? Of course, we've already learned quite a few things. So for example, we know that there's a beautiful relation between the giant planet occurrence and the as a function of the mass of the host star. So when the host star becomes more massive in the range, then the chance to have a giant planet also increase. And with this very beautiful linear relation, probably because if a giant larger star, you also have a larger disk, and then you can form more giant planets. But this relation kind of have some problem when you increase the range of these host star mass. And actually there are some discrepant observations about these giant planet occurrence in these slightly higher mass range. So for example, if you use the observation from subgiant and dwarf stars, you get a higher result, and if you use that from the giant stars, you get slightly lower result. And also theory have different predictions for these occurrences. And what's even worse is that if we extend this range of host planets to even higher mass range, then actually we'll know almost nothing about planets around these white dwarfs. So actually we only know two things. One is so actually we only know of two exoplanets like the round stars in these mass range. One is the first exoplanet discovered around the pulsar, right, by Alexander Wolfson, and who is sitting here today. And the other is perhaps from last year. There was one exoplanet detected around a B-type star, which is about 6 solar mass. And although we have like 5,000 exoplanets discovered today, but most of them are in the low mass range. And so what can we learn about exoplanet here? Actually, white dwarf, as mentioned by Lubaya this morning, white dwarf is a very good like window to really study these systems, because it just corresponds to white dwarf in the mass range of 0.7 above. Right, so we've heard about many things about like exoplanet, planetesimal around white dwarfs, and also accretions, pollutions around white dwarfs. But I would like to talk about the ways to directly see the light emitted from a planet around white dwarfs. Right, so here I'm showing the spectrum of white dwarf. Basically in the infrared band is power law. And the interesting thing about planet around white dwarf is that the giant planet can be larger than white dwarf because it have a Jupiter size, but the white dwarf has an Earth size. Right, so that means in some band, especially when you go to infrared, the brightness of this giant planet can be even higher than that of a white dwarf. So I'm overplotting a giant planet spectrum here, and as you can see, there's several features from the planet, and especially one interesting is within the second Spitzer band, that's around 4.5 micron, and there will be a very strong flux axis in this band. And also we know that absolute measurement is difficult, but luckily right next to this band, there's an absorption band of exoplanet atmosphere. So then we can use like the color axis between these two bands as a signature of our exoplanet. Right, and so that means if you want to use this method to detect detect exoplanet. We want the planet to be as bright as possible, and we want the white dwarf as faint as possible, and that will be related to the evolution of these two types of objects, right? And interestingly, the evolution of giant planets is very similar to a white dwarf. It's also a cooling process. So it was born hot, and then the time goes by, it becomes cooler and fainter. So here I'm showing like the cooling curves of different exoplanets and the cooling curve of a massive white dwarf. And we know that, of course, with the chance to have a more massive, to see a more massive planet is higher. And also, we want the white dwarf to be more massive so that it's fainter and also allow us to detect younger part of the system. So as a comparison, this is the cooling curve of a 1.1 solar mass white dwarf. You see the detectable region is becoming smaller. Right, so we want to basically see young and massive and nearby white dwarf and check their infrared flux around 4.5 micron. So this brilliant idea is of course not new. It was first proposed by Andrew Gould and Mukrmin Kilic about 14 years ago. And right after they proposed this idea, people also checked in a Spitzer survey and kind of a sample of white dwarfs. But unfortunately, they didn't find any signal. So that's why we didn't know any exoplanet around these white dwarfs. So then you might wonder, what's the point, right? I mentioned again today here. So basically, there are two reasons. One is after the 14 years of the first white dwarf program, so there are a lot of new white dwarfs observed because now we have a Gaia sample, right? We know a lot of new white dwarfs, and many of them are observed by chance in the Spitzer program, like the extragalactic programs. So the sample size now is a bit larger. And also the pipeline, photometric pipeline of Spitzer is becoming better than 14 years ago, especially for the calibration. Right, so here I'm showing basically the sample of these young and massive and nearby white dwarfs. So the light gray one is the Gaia sample, and the larger gray one, that's from the previous Spitzer sample, and the black ones are the new sample observed within the past 14 years. And you see that it's about a factor of 70% larger sample. Yes, to give you some sense of Spitzer observations, its coverage is not a whole sky survey, so it's only pointing to a few positions on the sky, is maybe about a few percent. That's why the Spitzer sample is much smaller than the Gaia sample. Right, so then with this sample, we can just plot what we want, which is the color axis. And so this x-axis here is the color axis in terms of flux ratio. So compared to model, to white dwarf model, okay, which means if it's around 1, that's consistent with model, and you see most of them are consistent with 1, and a few of them have excess, which might be from exoplanets. And of course, here I already removed like contaminations from other infrared galaxies, which have much higher excess. Right, so you see these 4 probable candidates, and so we can plot the theoretical the expectation for a planet signal, right? From the brightness, we can kind of infer the mass of the planet, and it's kind of within a reasonable range of about, so this one is about 6 solar Jupiter mass, that one is a bit higher, and the 2 a bit lower. Right, so then of course we also want to do some sanity check. So this is the flux axis in the Spitzer first band, and we don't expect to see any flux axis because there's an absorption band there, and indeed you don't see that. And also we check the J band photometry, and again, it's kind of consistent. Right, so that's basically the result, and yeah, so nothing complicated. And so then I focused on this one object which have the highest signal to noise, and checked some details of these white dwarf, and interestingly shows kind of also weird signature. So it's a very massive white dwarf and very bright because it's young. And this is the LCD. You see that there's an axis in the 4.5 microband, but not the other band. And so in Kavli's catalog in 2020, the spectra have low signal noise, so it's hard to really say the classification. But thanks to Ilaria, she shared information with me. She had a lot of observations, spectral observations of massive white dwarfs. So if you want to use one, don't hesitate to collaborate with her. Right, so from her spectrum, we know actually it's a dB white dwarf, and also it has very strong magnetic field. I don't know what that means. Perhaps it's a merger, but then how that is related to exoplanets is still a question. Right, and also we checked like the photometric variability and from ZTF and also TESS, and it seemed to be a variable white dwarf with a 10-minute period, about 3% in amplitude. And again, it seemed to be a indication of merger, but not clear how that relates to planet. Okay, so it's time to conclude. So today I talked about exoplanets. There's a big hole of exoplanet detection for whole star with a massive mass range, and white dwarf is very nice system to really study them. And I talked about possible, detections of infrared access using Spitzer, and then we find one candidate. And if we add those like 4 candidates all to these plots, we might have some like slightly increasing trend of occurrence rate. And again, this region is actually very difficult for theoretical prediction. So actually there's no theory yet for predicting these planet occurrence. So we really need a lot of observations and also new theories to do the comparison. And it didn't mention that, but actually this system, if it's confirmed, if it's true, actually it's an ideal system for observations of JWST because it's nearby and around white dwarf, it should be far away. So there's a high possibility that you can resolve it. And also white dwarfs are very faint, so you don't even need a chronograph. You can just take a photo of it. Right, okay, that's all.
Thank you. We already have one question.
Could you go back to the SED type plot?
Yes.
So you have an excess in the far infrared, but you have discrepancies at almost all wavelengths.
Yes.
So a planet wouldn't do a deficiency at 4 microns or so. So I don't know. It just clearly the white dwarf model doesn't fit.
Right. So that's a very good question. So this white dwarf model is, I think, is using either DA or DB, but not yet considering the magnetic field, because at that time I didn't know that it's a magnetic white dwarf. Yeah, but with Ilaria's spectra, I think we can do much better to fit this SED. But the problem is, I don't think any other process can really create an axis in infrared, right? I imagine that there's some possible cyclotron emission. Yeah, that's one possibility. But otherwise it's hard to really get a lot of infrared. This is 50% more infrared access in one band, but not the neighboring band.
We do Ingrid, Ken, and then Ilaria.
Mine as well. I was going to ask if you considered cyclotron hubs. So, yeah.
Right. So I think probably cyclotron emission is, yeah, that's a possibility. But that means you have some material also around the white dwarf, which might also be interesting. Yeah, but it's just not as interesting as a planet, probably. I don't know.
No, I checked in Galax, and I don't know where this comes from, but with the SCD doesn't look particularly. I have the SCD for this object, and it doesn't look any weird. I don't know which models is that from, but
Okay.
there's no excess in the UV, for example, or looks fine.
Thanks.
Sorry if I missed it, but well, why can't it be a disk? Is it too red?
I mean, is it possible it's a disk? I think it's unlikely, because if it's a disk, then the infrared, the neighboring bands should both have access. It's not easy that one band have 0 access, but the other have a 50% of access, and the wavelength is very, very close.
Did you check the chance of just having a background galaxy in there? Because when we did this originally, we had the other Spitzer bands, and here you don't have that, right? So you don't have any data beyond 4.5 microns. So you can't necessarily see if the SCD is rising more, you know, what it's doing.
Right, so I think there's 24 micron, 12 micron, but the signal noise is too low to really see any, even the white dwarf, we cannot see that. So yeah, so unfortunately, there's
okay,
no
but I mean,
way.
you could still check the chance of just randomly having a background galaxy in the aperture and see what that is, because you're looking at, I don't know how many targets you have in total, but there could be a significant chance that you would end up with a background galaxy in the beam, right?
I see. But for background galaxy, do we also expect like a sharp?
I mean, it depends on the redshift, right? So if you have high redshift, it could, because from Harvey's images, we see that they do pop up in the infrared, yeah.
I see.
Thanks, Sihao. So I know WD 1856 is old and low mass, but do you think it would be a useful calibrator here, like looking at it in Spitzer if it has the photometry?
You mean using Spitzer as what, to observe the old system?
Maybe just to sort of like calibrate this. Like I don't know if it would be like a useful kind of example or reference point, maybe.
You mean to calibrate the current rate, or to calibrate the Spitzer photometry?
Maybe. Like I'm just wondering if you could do this experiment with it, since we know it has a close-in, potentially giant planet. It's a different parameter space, being low mass and old.
I see. Right. But unfortunately, I think the problem is for the old system. The white dwarf is also not massive, right? So the white dwarf is much brighter, and also the planet is much fainter. So kind of the expected access, I don't have a number, but it might be just a few percent, which might be too small for Spitzer, because the Spitzer calibration error is around a few percent, right?
Okay, very quick last question.
Have you, are you going to look for pollution of photosphere of the white dwarf, just to check and make sure it's not a debris disk?
Yeah, so actually these white dwarf might be very far from the planet might be very far from the white dwarf. So
no, I understand, but the debris, if it's excess is due to debris disk, it's going to be close. So just as a double check, I mean, I think you're probably right based on what you've said, but to be, safer, just look for heavy elements in the photosphere of the white dwarf, and then if you don't see any, then you can be sure it's not a disk, because all disks pollute the white. There's no example, essentially, I think, maybe one somewhere hidden, I don't know, but basically there are no examples of infrared excesses and not having pollution of the photosphere. So it's just a check to make sure you're not fooling yourself.
Yeah, I agree.
Okay, yeah, we have to move to the next speaker. Thank you very much.